Okay, Avenue Code, day 19. Hopefully better than yesterday. We have workflows and part ratings. Select all the parts, add together all the rating for accepted parts. Okay. Let's see. Okay. XMAS. Okay. XMAS. 19114. Okay. Oh. 1 to 4,000. Low, A high, S low, S high. Q dot pop left. I see Xmas. Beautiful. Let's see. message. Sure. See. That is wrong. in how? One, 6, 7, 4, 15, 15, I think. Okay. That went tolerably well. Yep, cool. So what was going on here? Also, this was a very ugly way to do part 2. Surely there must be a nicer way. Anyway, so we are given this list of the state machine. So this says if you're in the state in, then apply the following list of rules. If S is less than 1351, go to state PX. Otherwise, go to QQZ. This one's more complicated. If you're in state RFG and S is less than 57, then go to GD. If X is greater than 240, then go to R. Otherwise, go to A. Right, so you're in some state, you apply the rules from left to right, and the rule can either be go to, or it can be if some condition go to. So we need to sort of implement this thing. In part 1, we implement it on these specific given points and figure out which ones end up in the state A. And in part 2, well, okay, let's talk about part 1 first. So, this is part 2. This is part 1. Right. I left a bunch of debugging print statements in. Just comment those out. So this prints out 418, 498, and 12333 603. Cool. Okay, so what's going on in part 1? So in part 1, we go through all of the parts. We like parse them into, X, M, A, S. So we strip out the braces. I guess maybe we could have just evaled this. We, take the thing to the left of the equal sign, take the thing to the right of the equal sign. We start in state in, which actually is irrelevant. Okay, so then we check if the part is accepted. And if so, we add its coordinates to our answer. So how do we compute if something is accepted? So we always start in state in, and then we apply the rules. So sort of while we are traversing, if we haven't reached the end, we go through the state machine. So look up the rules for our current state and then apply them left to right. So figure out, so the rule says, conditionally go to a spot. where the condition is either it always happens, or if there's a colon, then it conditionally happens. So if there's a colon, then figure out, so there's some destination and there's some condition. The condition is a variable, a greater than or less than, and a number. So if the condition is greater than, then we check if our variable is greater than that number. Otherwise, we check if we're less than that number. And then if we're supposed to follow this rule, if we're accepted, return true. We're trying to figure out if we're accepted. If we're rejected, return false. Otherwise, go to the next state and break, because we're now done, right? Once you actually execute one of the go-tos, you don't keep applying the rest of the rules. And if we're not done, right, if the rule doesn't apply, then we do keep applying the rest of the rules. So that'll take us from state to state until eventually we get to either A or R, A being accepted, R being rejected. And then for each of the accepted things, we add up their coordinates. So that's part one. Part two is tricky. It says, let's assume that we have parts rated from 1 to 4,000 for each of these four variables. How many of them will be accepted? So we can't brute force this because there's 4,000 to the 4 possible parts, which is what, 256 quadrillion? No, 256 trillion. Sorry, 4,000 to the 4. So that is too many to check one by one. So we need to do something smarter. So we can just follow all paths in the state tree is the idea. So we start out in state in, and some of the parts have s less than 1351, and in which case they go to px, and some of them have s greater than 1351, or greater than or equal to, 1351, in which case they go to QQZ. So we're going to keep track, we're just going to follow all paths in the tree, and sort of a given location that we are at, right, we have, so initially we have we're in state in with all of the parts. And that's what we're going to keep track of, is we're in some state, and here's what had to be true of the part to get to this state, okay? So that's the idea here. And so if we're in a state with no parts left, then we don't need to keep processing this subtree. If we're in the state of being accepted, then all of these parts, right, so we're supposed to count how many parts are accepted. So all these parts are good. So how many parts are there in this range? And maybe I should find a nicer way to do this. I don't know. Anyway, this is the number of, so the number of parts is, there's some range of x, some range of m, some range of a, some range of s, that, all these parts that we're looking at right now are. So there's this many values of x, this many values of m, this many values of a, this many values of s in this subtree, and they all are accepted. If we are in a rejected state, then none of these parts are accepted. Otherwise, we need to sort of keep going down subtrees and sort of follow our rules, which will partition the current set of parts into smaller sets of parts that follow each rule. Right, just like I said before, we start out with all the parts in, and then we partition the parts into two piles, one of which goes to px and one of which goes to qz. So I have this ugly way of doing this, which, let me just move the part 2 stuff down to part 2. Cool. All right, should I talk about the parsing? The rules on the parts are separated by 2 new lines, and then for each rule we're just going to figure out the state name and then the rules. So that's what we're computing here, that mapping. Anyway, so how do we actually sort of split the parts into piles? Well, we go through and apply all of the rules. So the simple case is just a straight go-to, in which case we don't need to split the pile any further, and we just go to that new state. Otherwise, we actually have a rule, And we need to now the parts are split into two piles. The pile that follows the rule, that goes to the state, and the part that doesn't, which continues processing the rest of the rules. So parse out the condition, just like before. And this is sort of figuring out the new pile that follows this rule, and they go to that state. And otherwise, we have the leftover pile, which follows the sort of negation of the rule. I've just introduced new operators, right? The negation of greater than is less than or equal to, and then the negation of less than is greater than or equal to. So this is the pile that did not meet this condition, so they keep processing the remainder of the rules. Right, so like from RFG, the things that go into R are both they didn't follow this and they did follow this. So there's like two conditions. And same for A, right? They didn't follow this and they didn't follow this. So this splits the pieces into three files according to that. Okay, so how does this? So new ranges takes a pile of parts defined by this horrible list of 8 numbers and gives you back the new pile of parts that actually complies with the rule, depending on the depending on which variable we're looking at. It's going to affect like that range of parts, right? If we have a rule about x, then we're going to have the intervals for m, a, and s are unaffected. The interval for x is affected, and it's just affected. So if we started with a parts with range high, what parts So this is like we had some interval, for x in this case, and it was supposed to be greater than something. So what are the what x range is greater than? Well, x must be at least something. It must be at least n plus 1. So instead of going from low to high, it's from the max of low and n plus 1 to high. Right? If we were already, say, the parts from 10 to 20, and we said now they had to be greater than 5, that does nothing. They were all already greater than 5. But if it's greater than 15, now it's just the parts from 16 to 20. So max. Similarly, if it's less than, that's bounding the upper range you might need to throw away. High is now the min of high and n minus 1. And then because I'm negating, right, so whenever I see a rule, some of the parts follow the rule and some of them don't. So I introduce greater than or equal to is the negative of less than, and less than or equal to is the negative of greater. Right, in which case, similar to the rule for greater, like now we need to be at least n, or at most n, and then just return the new range. So if we were a condition on x, change the x range. If we were on m, change the m range. A, change the a range. S, change the s range. Return the new big list of ranges. Right, so now there's some more piles. This is the pile that met the condition, and then the pile that didn't meet the condition, we keep following the rest of the rules. So that sort of splits all of our piles according to to this tree, right? So we're just following the entire sort of work tree, all possible paths a part could take through the tree, and at any given time, we have some like big pile of parts that are still following the rule, and so I don't know, we are actually processing all 256 trillion parts sort of at once, because these piles are going to be very big. But we're not keeping the pile part by part. We're just keeping the pile as a list of ranges. So that keeps things manageable. And I don't know, apparently there just aren't that many paths through this tree. I guess we could count if we're curious. This is going to be something. 1600 paths through the tree? Sure. So, yeah, can't process all 256 million parts, but we can process, you know, all the like possible ways a part could get accepted or rejected and count how many parts sort of follow each of those ways. So that is how to do part 2. And that is it for today. See you tomorrow.